For this lesson, I'm really thinking about volume in terms of big and small. We're going to look at the huge range of size of matter in our world that if we are scientists and we're taking this on, we have to consider. So what I'm going to do on this scale is put human in the dead center, because this is where we are, and we can look up at things bigger than us, and we can look down at things smaller than us. Lesson number 3 is focusing on scale. The point of it is to, first of all, just look at the huge breadth of scale that is in our universe, from solar system and universe all the way down to atom and electron. Ant. So maybe near flea. Can we get smaller than bacteria?
Atom.
Atom. I heard cell. So I wanted to give students a chance to kind of sink into the difference in size. What we're doing is we're comparing very different things, right? These are separate individual things. Now let's go inside of one thing and sort of like to do an ocean. So an ocean is a massive thing. So what are some of the things that an ocean contains? Let's whales, great. What else can you find inside of an ocean? Salt.
Seaweed. Shells.
Seaweed. Okay, so now let's take a look at our list, and let's make a little category here for one of these things. Which ones are alive? Whales are alive.
Fish.
Plankton. So what we're going to do here is just keep getting a little bit smaller and smaller and smaller. And then could you go deeper into the tail and see something smaller in the tail? Bones. Bones and muscle and cartilage. And then eventually you would get to cells, right? You would get to cells. So I'm just making the point for the first time with students here, is that something that is alive is ultimately made up of cells. The thing that I basically want to get to with students here is that things that are alive are made of cells. So what are things that are not alive, like water and salt and rocks and sand? They're not made of cells, so what are they made of if we zoom into them? The sort of second point, just besides the vast scale of matter that exists, is the atomic theory, which is that everything is made up of atoms. And that these cells are made up of atoms, but water is also made up of atoms, and salt is made up of atoms. That it all comes down to atoms. So I wanted to introduce that fairly early on because it's going to be a controlling topic for a couple lessons in a row. I'm hoping that we're building a definition of matter. In lesson 2 we talked about how matter was something that had mass and volume, and then in lesson 3 you get to the idea that matter has mass and volume and is made of atoms. So we built a little bit more onto that. That's it? Okay. So now what I want to do is for you to hold up your identity of your plus and your minus charge. And I want you to act out the force that you are going to feel in response to the other charged particles around you. In this lesson, I'm trying to really focus on central concepts that I know are going to come up again and again as students go on to take science classes later on at the college level, and also concepts that build upon each other. So electric charge we did because we can apply that topic to the atom, we can apply it to how atoms bond to form molecules, we can apply it to a whole bunch of different things. Right, possibly. Yeah. So let's set up something else. Can I have the 2 pluses come up here? And face everybody, stand maybe about 6 feet apart. And Megan would be so Meg has a negative charge, so let's put you right in like the center. Mm-hmm. So what would happen to Megan now? She has these 2 positive charges here. What would how would she move? How would the force affect her to move, given these two?
Whichever one is or to the center.
Through the center. Through the center. Yeah. Great. Yes. So that's exactly right. So one other thing about this is that these two charges are charge is not plus is not stronger of a charge than negative is. They are equally charged. They have equal power. So they are both going to be pulling on her the exact same amount, which means that she's going to sink back until she's kind of stuck hovering directly in between them. Yeah, exactly. So she's not going to go, she's going to be like hovering. And oh, you guys are demonstrating this perfectly as well. That's a highlight of the lesson. It's really fun to do. You can get pretty dramatic with it. Students or teachers or whoever's participating, they really have to apply the concept by acting it out. So one other thing about the summary or putting it into words, I do think it's actually easier to have students talk it out with a partner. Okay, talk it out, explain what those the concepts were, and then maybe take some notes. I think that's probably a better way to go about it, actually, because it's easier to sort of say something before you put it down in words. So we're going to actually move on to the next lesson. Up to this point, the last 3 lessons were physical properties and physical change, and then we looked at change of state, and then we looked at electric charge as a physical property. We are now moving into the structure of the atom. Remember yesterday we were talking about the ocean, and we made a really nice list of all of the things that are inside of an ocean. We identified that some of these things that were alive were made of cells, but that absolutely everything was made of atoms. So now we're picking that back up. We're going to come back to that idea. I think that this is probably the most essential lesson in this lesson set. The structure of an atom dictates a lot. It's just an underlying foundational concept. So this is an unusual lesson for me. I taught this a couple times. I just felt like I never really, it was just always overwhelming and confusing. And I finally decided to introduce the structure of an atom in a very particular way. What I found from working on this topic with students is that they don't have necessarily the background knowledge on it. So I introduce it in a very, very specific way, introducing first a basic model of an atom, of just a heavy nucleus in the center surrounded by a cloud. They take notes on a template while I'm speaking about this, and then we look closely at what is the nucleus and what particles are part of the nucleus. So the nucleus is made up of 2 kinds of particles. Here we have a proton, and we have a neutron. Now, a proton is important positively charged. Another important thing about the proton is the number of protons in an atom give this atom its identity. So that means if you have an atom and it has 2 protons in it, no matter what, it is going to be helium. So what can you guess about the charge of the neutron based on the word? That it's neutral. And how did you know that? Because the prefix, right? You see that neutron has the same beginning as the word neutral. So a neutron has no charge, but it has the exact same weight as a proton. It weighs 1 AMU. And the number of neutrons can change in an atom, but it doesn't change the identity. And then we look closely at what the cloud is and the structure of the cloud and what particles are part of the cloud. So the electrons are kind of whizzing all around in a cloud formation, constantly in motion. There are different sort of layers to it. And these layers can only accommodate a certain number of electrons. So for the first layer of this cloud can only accommodate 2 electrons. So this open circle, I'm drawing this open circle as if it's an open seat. It's unoccupied as of yet, but it's an open seat for an electron. The way that the electrons fill these seats is very specific. They're very orderly. They always start with the closest seats to the movie screen, or the closest seats to the nucleus. They always fill in these first 2 seats first before they start filling in this next row. I then asked them to apply that knowledge by building a model of an atom of helium and an atom of oxygen using stickers, different colored stickers for the protons, the neutrons, and the electrons.
We'll cook them. Yeah, cook them. Right. Oh, put an N on the sticker. So they're neutrons.
What does it say about me that I went right to my electrons?
I like this activity in the classroom a lot because as they're building it, it's very easy for me as the teacher to walk around the room and see who gets it, who's putting the particles in the right place, and who's putting them in the radically wrong place. So I can very quickly kind of assess their understanding of which particles go where.
So then what about the ones in the second ring? Mm-hmm. How would they, so they would stay over here and over here if there were only 2 in the second ring? They would try to stay as far away as
but
they
they're
could?
constantly in motion, so they're basically constantly whizzing around trying to avoid each other, trying to be as away from each other and as close to the positive nucleus.
So the rest of
Okay, so one thing I'll say about this activity is as you walk around the classroom, it gives you this instant visual about who understands where which particles go and where the particles don't go. Okay, and it leads to some good conversations in groups. Is this atom overall charged or neutral? Neutral. So why is it neutral?
Balance of electrons and protons.
Balance of electrons and protons. There's 8 protons positively charged and 8 electrons negatively charged. So if you remove an electron, you have 1 less negative charge. It would have a +1 charge. This is something that has to be illustrated for students on the board. But right now, this atom is neutral. So neutrality is important to matter. Matter wants to be neutral. It tries to be neutral. For me, it was really about calling back to previously taught lessons as much as I possibly could and linking them all together, and this kind of constant awareness that we are still talking about stuff, we're still talking about matter.